So if I'm getting you to watch this video, I think you probably have seen how we trace a search, at least depth first search, maybe other searches too, using the table notation in a frontier. And what I'm going to do in this video is just show you a couple of other ways that we might go about visualizing a search, and also some tips on how to write this in code, which you'll have to do at some point soon. So here's the our generic code for how we do a search that has been edited for depth first search, and that means that we are using a stack for our frontier. So here is a sample graph that we're going to use. The graph doesn't have any cycles, so it makes it a little bit easier for us to do this. But as you can see, it's got a start state up here that I also have indicated by this triangle. And I'm indicating the goal by using a double circle down there. So the first way that you can visualize or trace this is to do it the way you've probably seen already, which is use a table to keep track of the frontier in the stack. So if we're doing that, we're going to, here's our table, we're representing the frontier. The top of the stack in this diagram, I'm always going to show on the left. So we start with just the start state on our the path representing the start state, sort of an empty path, I don't know, or a single path that just has one node that doesn't go anywhere, a path of length 0. And then we pop this off of the stack, and we say, is the end of that path the goal? No, it isn't, so we're gonna keep going and expand that. So here's our table. I've already initialized it with the 0 length path that's just the start state, right, A. And what we do, of course, every iteration, we pop this off the stack. We look at the end of this path, which in this case is A, and say, is that the goal? Nope. And so we say, who are the neighbors of A? Well, there's B, C, and D. So we're going to push back onto the stack AB, AC, and AD. So when we expand it, we discover it has 3 children, B, C, and D. Or three neighbors, right? So we take the A that we had originally, and we take AB and push it on the stack, so it ends up at the end, and then we push AC on the stack, and then we push AD on the stack. So next step, we pop the AD off the stack. We say, is D the goal? Nope. And so then we keep going, and we look at the neighbors of D, which of course, there's only one neighbor, which is F. So here you go, and of course AB got pushed first, just because I arbitrarily decided to push them in left to right order, and therefore the next thing that we're going to pop off of here is AD, right? And so I pop it off, I say, is D the goal? No, D is not the goal. A goal, I suppose I should say, right? Because it could have multiple goal states. D is not the goal, so I say, who are D's neighbors? Well, there's only one, that's F, right? So we're going to, I popped this off, and I'm going to replace it with ADF, that full path. So here's ADF, right? We pop this off the stack. We say, is F one of the goal states? No, in this case, we only have one goal state, but really we're just going to say, is F a goal state? And so we look at its neighbors, and remember, sometimes some people call these the successors of F. We call them the neighbors. Only one neighbor, H, so we're going to push back, ADFH. Here's my ADFH. I am now going to, well, here is my frontier at this point, right, which is a stack that has AB at the bottom, AC next up, and then this ADFH path at the very top of the stack. So we pop this ADFH off the stack. We say, is H the goal? Nope, H is not the goal. Who are H's neighbors, right? Who are the successors of H? Oh, look, H doesn't have any neighbors. And so we just throw it away. This guy, where's my pen? There we go. This guy that we popped off the stack is now gone, right? We're not going to replace it with anything. And so these two are going to move up. So there you go. Here's the next step. And now we are going to pop AC off the stack. So we pop AC off the stack. We say, is C the goal state? No, C is not the goal state. So we say, who are C's neighbors? Who are C's successors? That would be F. And so we add ACF onto our frontier, right? We push that on. And now, of course, we're going to pop that off. We say, is F the goal state? Nope. So we're going to say, who are F's neighbors, the successors of F, and that would be H. So we're just going to add ACFH onto our frontier, right? And so now we pop this off the frontier and we say, is H a goal state? No, it's not. So, so we don't push anything. Oh, so we look for the neighbors of H. It has no neighbors, and so we just don't push anything new. So this was popped off, and we're going to be left just with AB on the frontier. Okay, so AB is on the frontier. We pop it off, and now we say, who are the neighbors of B? Oh, sorry, is B the goal? No. Who are the neighbors of B? We take a look. Neighbors are E, so we're going to push ABE on the stack. Now, it's important to note, as I say in here, that this is a goal state, but you only determine it's a goal state when you pop it off, right? So what we have to do, this is on the frontier still. We pop it off of the frontier. We say, is E a goal state? And hooray, it is. So we say success, and we draw, you know, some very cute picture that I can't do right now, but there you go. That is not a cute picture. That's a creepy picture. There you go, success. Okay, so we have found a path. Our path is the last thing we popped, which was ABE, right? ABE, beautiful. Okay, so that was one way that we can describe and sort of keep track of what we're doing, trace what we're doing when we are trying to solve a graph. But another thing that we can do is to use a tree trace approach. So let me just show you what that looks like. So I'm going to try and show it to you in parallel with our standard frontier approach, right? And the basic idea is whenever anything is on the frontier, it also somehow appears in the tree view. So to start out with, we have the start state there, and we've got our initial root of our tree here. And so the next step is to say who are the neighbors of this root, right? We're doing the same thing that we would be doing in here. We're just sort of drawing it visually, and the neighbors would be B, C, and D, right? And so we add on to our tree B, C, and D, right? And now we pick the first node that we're going to follow because, of course, we're popping it off of here, and I want to do things in the same order as this. And we're doing depth first search. I'm going to expand this node in the tree, and so I pull this off and I say, first thing, is D the goal? No, D is not a goal node. So then I look, who are D's neighbors? D's neighbors are F. So there you go. And so we add F onto our tree, right? It's pretty much the same. We're doing the same thing as over here. It's just, you know, we're drawing it instead of so that we can see what the tree looks like. But it's very common for people to draw these trees, so I want you to sort of see this notation. Anyway, we pop F off, or we take F and we examine F, right? We're popping it off the stacker. We're looking at this one now. We say, is this the goal? No. So let's look at the neighbors, H. So we've got H. We now examine this one, sort of pop it off, right? Is H a goal? No. Who are the neighbors of H? There are no neighbors of H, so we're gonna, this path is sort of dead to us now, right? We can't really do anything with it. So we're gonna start examining this this C. Who are the neighbors of C? Well, it's just F. Of course, C expands into that F. So there you go. We've added ACF to the tree. And it's super important to note here that F appears just once on this graph, and this arrow is totally bizarre. Here's where F appears on our graph, right? Forget that green arrow. But it's actually on our tree twice, right? So essentially, this path ADF H, this F is represents ADF, that kind of the path you're following, whereas this F represents what happens if you did A and then C and then F. So it's just important to understand that while there's only one F in the graph, you could have multiple ones if there are multiple paths in there. Anyway, let's continue our tracing. We are going to examine the neighbors of this F. So we add H to the tree here. And again, notice we've got two H's, but that's not a problem. This one represents a CFH path. This one sort of represents the whole path, a DFH. And we totally get it. That's not a problem for us, right? So we say, all right, let's expand this H. Is it a goal? No, it's not a goal. Does it have any neighbors? No. So now we just have to keep going. We're expanding this B now. Does it have any neighbors? Yes, it has an E. So there you go. Our E is on there. Of course, we don't recognize that it's the goal yet. We have to wait until we say, all right, let's expand this. But before we expand it, check, is this the goal? And we say, woohoo, it's the goal. And so we say, all right, our path is A to B to E. And we try again to draw a smiley face. Ooh, there might be some hope here. All right, it's a strange smiley face, but a little bit better. Okay, so that's the regular tree view approach. But wait, there's more. There is also a colorful tree trace, right? So, and it's really important if you cannot see that these are 4 different colors. I don't know, do you call black a color? Anyway, if they do not look different one from the other, then you need to let me know. Please let me know if you're colorblind. Send me an email or something, or tell me after class, just so I know, because you're not going to be able to quite get this. We don't need color very much in this class, but this is one of the places where the textbook actually uses different colors. Okay, so in colorful tree view, basically, we start with our entire tree all drawn out, that whole paths, all the possible paths through the through this graph, right? Which is actually a kind of an unrealistic thing to do, but it's the way your book tries to explain stuff, so we will do that. And then we just sort of color in nodes as we go. There is sort of an advantage to this in that at least in the colorful tree view, you can see whether we've sort of explored a node or not. So I'm just going to go through this relatively quickly since it's almost exactly the same. This A we color in green because it's our start node. And then when we expand A, anybody who is at the end of the a path on the frontier. So for example, AD is a path on the frontier, AC is a path on the frontier, AB is a path on the frontier. Those nodes that represent the ends of the path, they get colored in with red. And so obviously we're going to expand this next. And what happens when we expand it in this colorful approach is we say, okay, D has been expanded. It's now sort of explored, we'll say, and F turns red. So in this approach, it's kind of nice because you can, in fact, the book actually does sort of circle things and say, all right, that right now is our fringe or the end of our frontier, right? That's the end of the paths on our frontier. So you can kind of say, okay, maybe this is useful, maybe not so much. Anyway, but I do want you to understand what the book is showing you. And so these blue guys are the ones that have not been expanded yet. So let's just continue. And you can kind of see what's going on here. So, of course, we finally get to this point. We need to expand this B, right, which actually corresponds to this point on here. It only has one neighbor. Right now, this is just a normal path on the frontier, ABE, nothing special about it until we decide to explore this one. That's the point at which we realize that it's the goal, and I've finally gotten smart and pasted in a sort of cute smiley face, maybe not, who knows. Anyway, that's the sort of colorful tree approach that your textbook uses. For the record, the textbook tends to draw the trees in any old way. I kind of like trees with the root at the top, but I understand that when you put the root at the side, sometimes it fits in a book better. And here's actually the graphic from the textbook that they're trying to use to explain to you what this looks like. Now, I mentioned this before. If you have any sort of real-world graph search problem, it's usually not very realistic to compute the entire colorful tree ahead of time, right? And figure out what all of these things are. See if you can think why. You might even pause the video for a minute and think for a second before I give you the answer. And the reason, of course, is if your graph actually has any cycles, if you think about it, if I have a graph, maybe I have A goes to B and goes to C, and maybe B goes to C, but maybe B goes back to A. Actually, maybe C goes back to A too, just to be crazy, right? So then if I'm thinking about all the paths through this, there's an infinite number of paths, right? Because if I'm drawing a tree, now I've got my A, which has children that are B and C. But then if I go to expand B, I end up with A, that's an A, and C. And then maybe I go, if I'm doing a depth first search, I go to expand my A, which has children B and C, and I never get anywhere, right? Right, so this is the tree that I'm trying to build out of this very simple graph. So even though I only have 3 nodes in my graph, my tree outline of this is infinite. So in general, what we do, suppose that A is the start state for my graph, and maybe even there's, an arrow from C to D, which is the goal. But what we actually end up doing is we just, walk through this slowly. So, I start with the root of my tree as A, I expand it, and I get B and C. And depending on what kind of search I'm doing, maybe I'm not doing depth first search. So maybe I'm expanding C again. I might get A and D, and then maybe I'm expanding A next for some reason. So, I get B and C, but then I'm lucky, I'm not doing just plain old depth first search, and I say, all right, let's do D. Oh wait, D's a goal, woohoo! And so we're done. So that's all great when you're trying to do this on paper, right? But when you're actually writing code, what we want is when we find a solution to our problem, like say, for example, in this case, my solution is the path A to B to E. What we actually want is to be able to tell someone, all right, go from, A to B to E. But if we're using a tree, there's no back arrows, right? So it's great. We've traveled all the way down here, but we can't get back up again. So let's talk about how you can actually implement this. So just remember our formal definition of a state space problem that we talked about. We have, here's just an example graph that I've drawn again, just so you can see, so we have something to kind of work with. And so when we're talking about our state space problem, right, we have some states, right? So in this case, that would be A, B, D, E, whatever. One of these is designated the start state. I'm using this little triangle. So A is my start state. Each state has a list of actions available in that state. In this example, I'm going to say that like A can go right or A could go down, right? And B could go right or up, and so on. What else? We have an action function, right? So if I say you start at B and go up, you end up at D, or you start at B and go right, you end up at H. And we have a goal function, which basically which takes a state like K and says, is this the goal? No. Is this F the goal? Yay. You could also have a cost function in here. I'm not going to explain how to implement that in your program, but I think it'll be pretty obvious once you get it working without the cost. So here's that same graph again. I hope it's that same graph. And I've tried to show you just a couple of Python code fragments that really are just to sort of give you an idea. So I'm going to have some sort of a class state, right? I don't know what my state is. Maybe my state is a room, or maybe my state is a room in which the package has been picked up, or maybe my state is a particular picture, a particular state in that peg game where I have 3 pegs left. Whatever it is, you may have to implement the state. It may just get implemented for you. But we have a class. There's some kind of a class for our state. There's some kind of also a class for our actions. So as I said in this example, the actions are going to be left, right, up, down. Sometimes the actions might be jump, swim, or fly, right? All sorts of different possibilities for actions. But I just want you to know I have a state class, I have an action class, and here's sort of the UML diagrams for the class. Basically, state is a class, it's got a bunch of attributes, a bunch of methods. Action is a class, it's got a bunch of attributes, a bunch of methods, woohoo! And here is our simple path node. And actually, the UML gives you more information than the init from the Python, because, of course, Python doesn't actually have any strong typing. But so, when we create a new simple path node, we take in a state. Well, here, let's do it over here. A state, which is of type state, right? Or we hope it's going to be of type state. Python, of course, would let you run it with anything because Python doesn't require you to tell it what type it is, but let's just say that you actually do it correctly. And you have, so your state parameter is of type state. My parent is going to be another simple path node, and action from parent state is going to be one of these action objects, right? And then the init is just setting up the initial attributes, the initial what would be private variables in any other language, but I have these pluses here because in Python they are public. And so assuming that you have written, you have that code set up, then you can do something like this. And so what I've done here is I've just tried to create a bunch of variables so you can get an idea of what this might look like. Of course, in any regular program that you do, you're not going to be making a variable P0, P1, P2, P3, and what have you, but I just wanted to sort of show you what this might look like. So let's suppose that we say, all right, look, we've got, I can't really write this so small, I need room. P0, all of these that I'm going to be drawing is is something of type simple path node. That's what that's supposed to say, SPN. It has three variables, right? If you look down here, you can see our simple path node. Actually, you can't completely see it. Oops, let's move over. There we go, right? But so it has, if we're looking at P0, it has A as the state that it's pointing to, and then we use these two values, none and none, which is the sort of Python equivalent of this space intentionally left blank, right? And when we make P1 is also a simple path node, and P1 corresponds to this B over here. And so we will have its state is B. Its parent node is going to be that P0, right? And how did it get from the parent node to P1? It went right, right? Because if you look on the original graph here, you start at A, you go right, you get to B. So that's where I came up with that. And so we can just sort of, if you go through, I'll draw a couple more of these, but then you can just sort of trace, and hopefully I've got it all right here. But if we do P2, right, which is an SPN, P2 represents K, this one right there. And so K is the state, right, with potentially all sorts of attributes and methods and whatnot. But this code will work for any old state as long as we have our state. The parent of P2 is also P1, right, because A is the parent, but to get from A to K, if you look at the picture here, you have to go down, right? So I wrote that in here, right? So there's the down, right? And so if you build up this linked list, then what you end up with is, for example, if let's just look at this A corresponds to this guy, which is P5, which is this, which has an A in it and points to P2, I hope, yes. And, oops, it shouldn't be red there. Sorry, I don't know how I switched to red. And it is also P5, the direction from its parent was up, right? In this thing, I wrote it as up. You can also see that to get from the K to the A over here, you go up, right, which is where I came up with this in the first place. If we continue this example just briefly, let me just show you one path through this, right? I'm not drawing all of these variables, but you get the idea. You could take a look, and hopefully what I actually wrote in the code there is correct. I was just trying to do it so you could see some examples. But if let's suppose that B is a goal, and we somehow do this path A to K to A to B, right, which is an odd path, but perhaps somehow we end up taking that early, then this last B here corresponds to P8. No, it does not. It corresponds to P7, right? So P7 is also an SPN. Its state is B. Its parent is P5. Oops, let's do an arrow there. And how it got from its parent was it went right. And so what you can imagine is if we finally decided that B here was our final thing, we could say, okay, well, let's sort of see what was the path that we wanted. Because remember, our ultimate goal is to say, I don't know, what are we looking at? So we're saying we went from this one to this one to this one to this one, right? So we want to say go down, then up, then right, which if we look at the graph over here, it's a little bit of a strange path. We go down, then up, then right. We do end up at B if that B happened to be a final state for some reason. It's not, I know, in this picture, but just so I can do this in a short picture, let's just pretend it is. Okay, you guys can pretend with me, right? Anyway, so then when we got to the B state down here, right, when we got to the B, we could say, hey, are you a goal? And if it was, then we could follow these arrows up and sort of keep track of, okay, the last thing I did was right, then up, then down. So if I flip those around and I go down, up, right, I'll get to my solution. Again, my goal in showing you this, in showing you the code from the previous slide, as well as this sort of these sample variables in here, was just to give you an idea of what I thought, well, what I recommend you might use as a simple path node to keep track of what's going on in here. I don't expect this to have been absolutely beautifully 100% clear. Maybe it was, but if it wasn't, watch this last piece a little bit just to kind of get a feel for what's going on in here. When it's time to write code where you need to figure out paths and figure out what are the directions, what are the actions that you need to take, you may want to just look back at this again, and you may find it helpful at that point. I hope so. Okay, enjoy.